So in this, we have, so this is Artin, problem 2.8. So let A and B so they are saying that if AB is invertible, then so A and B are invertible. So anyone knows how to do this? Arnab, what have you tried?
I'm just having some random ex- examples and just think, is it really right?
Okay.
I have not such process that actually meant that. I mean that actual process.
Okay. Think. Rohan, do you have any ideas? Anything, even if you cannot, you can use any theorem. Even if you cannot prove that theorem, it is not a problem. You can use it. It's a standard theorem, you can use it.
mean, I might try to multiply both sides with some like I'll call some numbers C or something as multiplicative inverse, and I'll try to multiply both sides.
Sir, can you hear me?
Yes, I can hear you.
Okay. Yes,
See
sir.
if you,
I have.
see,
Like, is my
Right.
voice breaking or?
No, it's fine. Yeah.
Okay.
Can you do
Okay,
this
yes.
problem? Can you do this problem?
Yes. Sir, we've already shown that it has a left inverse.
Which one?
Oh, no. One second.
So one of you has to do this, or together with few ideas. Like Rohan has given this idea that there is an inverse. C is an inverse. So let's see. Arnav, can you from here show that B is invertible?
Then I have to just take CA and apply
That's
it
it,
for
right?
the
Sir, yeah.
Yes,
Sir,
done.
we have CA into B is I. So B has a left inverse. So then it has a right inverse and has an inverse. Same, I think similar thing we can do for A, but we write A, B, C and then group BC. Same thing.
Right. Arnav, it's more or less done, right?
okay.
Right?
I'm
But
just asking you.
yeah, but let us see what are the things that make it work. Okay? So here we are saying that B has a left inverse. This implies B has a left inverse. So this implies B has a left inverse. So why does it imply that B has a right inverse?
So B is a square matrix, and there was a result. Like I'm not sure of the proof, but I know it uses row reduction. So if B has a left inverse, and B is a square matrix, then it has a right inverse as well, and the right inverse is equal to the left inverse.
Right. Good. So see, even if you don't know the proof immediately, it's fine that you're using it, using the result. Right? So you see, I'm saying this to all of you now, right? So initially I said, right, that like even if you cannot prove it's okay, you can use the result, right? That something has a left inverse implies it has a right inverse, and then both of them are equal. And then for A, you can do similarly. Okay. So then you can take this as homework and try this, and that will follow from the other things which we have done, but should try this. So a homework would be to show, and I'll say it in a way that you can use it in other places also. Right. So let X be in MNR. Okay. And okay, so anyways, yeah, let X be in MNR. If YX is equal to identity, okay, then show that there exists Z such that XZ is equal to identity. Okay, this is homework 1. You should try to prove this. You can also use determinants, or I don't know, maybe. And it's a very remarkable fact that one-sided inverse implies other inverse. The second homework is related, but so this again you should will little bit maybe out of the comfort zone, but soon it will be comfortable. So S be a set. This be a binary operation, an associative binary operation. Everybody knows what a binary operation is?
Yes, so just a function from S cross S2.
Right. Associative binary operation. Okay. Say the rest. So you see, it's very important to know why something is true, right? And why something is true is not just knowing the proof of it, but knowing what really is needed in the proof. So the next thing, which is like if left and right inverses are equal, it doesn't. So that is true, and probably you can prove it in many ways. But in the end, it only depends on the fact that this multiplication is an associative binary operation, and it doesn't depend on any property of matrices. So it's better that we prove it like that, so that when you do group theory, ring theory, it's true in most of the places. Not all places, but most of the places. So it's important, and therefore, when if you know it, if you know the basic reason for why it is true, then if it is true somewhere and you have not seen it before, still you will know if it is true there, right? And then you can probably prove it also. Anyways, so these things, S be a set and this be a binary operation, associative binary operation. Yeah, I'll just say with an identity. And show that left inverse equals right inverse and let me write it in a proper way. If BA equals AC equals E, then B equals C. Okay, so you should prove this. And then this will follow because matrix multiplication is associated, right? And multiplication is just a binary operation on the collection of all matrices. So these two things. This will also follow from one of the homeworks that we had last time, but we will not do it now. Means if you do the homework, then you will be able to see it. Okay, so just give me 1 minute. You can try this now also. Okay. Let's do one more problem like this, which is not there in Artin maybe. One second. Okay. So let S be a set, okay, and let there be two binary operations. Okay? For those of you who know ring theory, you will probably see that this is a ring. But if you don't know, it's not a problem. So there is one binary operation and there's another binary operation. You don't need any ring theory for this. Okay? This is just a set with two binary operations, just integers, something. Right. And obviously there is, not obviously, but there is also an one which is a multiplicative identity. One stands for multiplicative identity. Just treat it as a problem in binary operation. And 0 obviously stands for additive identity. So no need to say all that. And this. All right. Now let M, maybe it's fine. So M is now, there is a subset M. Okay. There is a subset M of non-invertible elements. Okay. M is a subset of non-invertible elements. And then there is a condition 1 that if S1 so we are collecting all the non-invertible elements in one place. Okay. Now there is an interesting condition that if S1 and S2 are non-invertible, then S1 plus S2 is also non-invertible. Okay. So M itself is like a nice thing. Yeah.
So is that given or do we have to show it?
No, it's given.
Okay.
It's given, all are given. And the second would be that if S is in S and S1 is in M, then S times S1 is also in M. Again, it's a very expected condition, right? So these are the two things. And now let us think if this is true. If UV is invertible, then does it imply that U and V are invertible? Similar conclusion we are trying to achieve.
So if suppose V is not invertible,
Hmm.
then UV will also not be invertible because U is in S and V is in M.
Yes. So you see, it's very easy, right?
Yeah.
Haha. Yeah. So this is just true. It's easy. Yeah. Everybody sees this. This is a very easy problem. Yeah. Basically, so the set of invertible elements is not, so you already know one thing which is universally true. The other direction is universally true, right? Product of two invertible elements is always invertible. Everybody knows that, right? If U has an inverse
Yes,
and V has an
so we just
Yes.
yeah, V inverse U inverse.
exactly,
We-
and
we
in
can
this
take.
in this situation, the opposite is also true. Okay, so the set of invertible elements is not just multiplicatively closed, but it's also in a way sort of saturated in these situations, right? It's sort of the reverse is also true. Okay, so these are very nice situations. Now, can you see, is this true for matrices? Because matrices have all these things. A collection of all matrices has addition, multiplication, everything. Are these two things true for matrices?
So second one is true.
Right, but the
From
first one is not true.
Yeah,
Yeah.
first one, yeah,
First
I'm
one
not
is
sure.
not true. Is not true. So you can use a
Okay.
simple counter example, right? Like 1, 0 and 0, 1.
And we didn't use the first property at all for the proof of the statement. So actually, the second one is enough. The second one on
Right.
its own.
Good point.
And
Good-
it's true, so that's sufficient.
Good point. Right. Correct. That's a good point. So you see, only with the second condition, yeah, you don't need addition structure at all here, right? It is just the multiplication structure. Correct. Right. And this thing is true for matrices. So Aryan, what's your reason? Why is it true for matrices?
So I thought about it using determinants. determinant of so suppose we have S and S1, then determinant of that will be determinant of S into determinant of S1, which is 0
Right.
because
So
S1 is in M.
yes, yes. So using determinants, you see this condition is true, and that's why it follows immediately. And this is what maybe I saw in the first place. I said you can use determinants. Maybe unknowingly, right? I don't know. But yeah, I know it already, so it's nothing to think. But you see, so just noticing this property about matrices is enough to conclude this. Okay. All right. Let me just think and make another question. Maybe we'll bring some nilpotent things into the picture and make a question. And I think that can make it also. So this is fine. So we want to reach the same conclusion, but maybe we'll change the conditions and slightly more interesting. Right. So let me, it's also going to be easy, I think, but let's just try it and see if. So we don't need this. So nilpotent element, you understand, obviously. And nilpotent just means that a to the power n is 0. So somehow here the additive structure also comes in when we talk about nilpotent element, because this 0 comes is really is this definition really comes from the additive structure, additive identity. So here is a condition: every element is, and this is very important in later studies. Every element is either invertible or nilpotent. So it's either this end or that end. Nilpotent is like the most non-invertible. So there is a dichotomy. So now can you show this? I think it is true. And later when we do Jordan canonical form and so on, you will see this condition holds for a lot of matrices, but not all.
So suppose U is nilpotent, which means not invertible.
Okay,
Then
I
U
think
bar
wait,
n is
wait.
0.
Wait, okay. So you don't say. Let's see if the others can
Oh.
do it. Let's see. And yeah, if you can do this, then some other question for you. So just others just play around with it and see. You can do it. It's not difficult. You see, Aryan has not seen this stuff, and it is, yeah. Just think neutrally and yeah. Yeah, to make some other question, it becomes very difficult. Not difficult, but
So actually, my proof it doesn't work for matrices. It works for commutative, where the multiplication is commutative. So
Okay, we'll see.
I'm actually
But-
not sure if
But you should not need commutative for this. So this is true general. And you can try to show that this condition implies the conditions of the previous problem. That would be a proof also, right? Yeah, that would be a good thing maybe if you can try. At least in the commutative case, that will. No, yeah, you will need commutative. So try to, so yeah, see. Anyways, let's, so has anybody done this particular problem then? Aryan, you can say the proof if you see it's correct. Say then.
so yes, assuming commutativity,
Without, okay,
if you
okay.
so
Anyway,
without, I'm not sure. I don't know.
I don't know. Let's see. So if UV is invertible, right? So if V is not invertible, so if V is not invertible, right, then V to the power n is equal to 0. But then UV is invertible, so there is a C such that this is identity. This is 1. After this, can we do anything? Hey, are you guys following? I'll erase this. Do again. Yeah. So see, we want to prove this, right? We want to prove this. So see, if U is not invertible, then what happens? We want to show that UV is not invertible or some kind of contradiction, right? Correct? So if U is not invertible, it implies that U to the n is equal to 0 for some n. Okay. So let's take the smallest n. You will need it, right? Let n be the smallest. Okay, let this be the smallest n. Okay. And if n equal to 0, then already you have a contradiction. UV cannot be 0 cannot be invertible. Okay, 0 is not invertible, right? Correct. That you can show. I mean, yeah, associativity you need. No, you don't need that. Yeah. Okay. Now what do you do? Your goal is to show that UV is not invertible. Show UV is not invertible. These kind of problems you have to go like this. You cannot directly show that it's invertible. Because what is its inverse? Can you write it down? No. So then how will you show? How will you get to that in the proof? Okay. Show that UV is not invertible. You have to use that U to the n and show that UV is not invertible. I mean, let's assume that UV is invertible. Assume that also you'll get some contradiction then. Assume UV is invertible. Rather just use this condition given, right? That UV is invertible. So then you have this, or maybe I'll use the right inverse. All this is there, right? All this freedom comes. Use the right inverse, and this is just identity. Now what should you do? Well, you do U to the n minus 1. Multiply by U to the n minus 1 on both sides, right? This is not equal to 0, right? Because n was the smallest.
Okay, because smallest. Okay,
They have to
yeah,
take the smallest, right? But this is equal to 0, and that's a contradiction, right? So what does it? What do we contradict? Wait, other people, Arnav and Rohan. So where is the contradiction? Think and tell. 0 is not equal to 0. So something. So we have a contradiction. So now what is the conclusion? So it contradicts one of our assumptions, right? And what is our only assumption? We have only one assumption, that U is not invertible. That's the extra thing we assumed. But that is not true, right? Which means U is invertible. Right? That is the only thing we assumed. Everything else we just used what was given, right? So U is invertible. Is it okay?
1 minute, sir, please.
Yeah. Take your time and think. There's no rush. Think about it, then we'll meet in 5 minutes, okay? Look at everything. And just one more
Yes.
homework that everybody can think about meanwhile in 5 minutes, or we can take a break, up to you. That show that this thing plus commutativity, right? Actually, it will imply the set of invertible elements has those properties. Those two properties which I wrote, right? That S1 and S2 are non-invertible means S1 plus S2 is non-invertible. And similarly, the other one that I wrote, invertible times non-invertible is non-invertible. You can show those two properties by using commutativity. And you won't need commutativity for the second property. And that is why you can do this problem using that problem, which is how you should do problems, right? If one problem is done, another problem is done after 5 minutes, you should use the previous one, right? Building on the techniques. Yeah. Solved problems is not a good solution. You should use the previous problem to solve this better. That's mathematics. Otherwise, you can't do mathematics, right? Very technical. It gets technical day by day.
So the commutativity, it's similar to the problem that we did on one of the earlier days, factorizing, like we can factor it.
It is similar, but I just need binomial theorem, I think. Think,
Yeah,
then
that's
we'll
what I
meet
was
in 5
thinking.
minutes.
Yes.
Then you tell the proof, okay? So yeah,
Yes.
so we'll meet in 5 minutes. Okay.